Okay, so now we look at collisions. And collisions are when two or more objects hit each other, or well, one object can break up into two parts also. We could also consider that to be the reverse of a collision, and this method works there also. Now we can classify collisions as either one-dimensional or 2D, or could possibly 3D. We won't be considering 3Ds, we'll consider 1D and 2D. And then we could also have contact forces being involved, which means that the two objects actually go and hit each other physically and then bounce off. So that would be like a car colliding or a billiard ball collision, so that would be an actual physical contact, or it could be through field forces. So for example, if you have a positive charge like a proton going this way, and let's assume another proton going this way, well, they'll repel each other and move off without physical contact. But this will also follow the same rules, and it's also a collision, and this is a very like an elastic collision. Now that's one way of classifying them, and another way is that we say that for collisions could be what we call elastic, which would be, this would be an example of an elastic collision. And in an elastic collision, the momentum is conserved, which means the sum of the initial momenta equals the sum of the final momenta of all the colliding particles, and this is conserved, and the kinetic energy is also conserved, which means the sum of the kinetic energy of all the particles before they collide is the sum of their kinetic energies just after they have collided. The second type, it would be the other one, which would be the inelastic collision, in which, well, the momentum is conserved, so the sum of momenta initial is sum of momenta final, but kinetic energy is not conserved, which means that the sum of the kinetic energy initial is not equal to the sum of the kinetic energy after the collision. In fact, the initial kinetic energies will also add up to be more than the final kinetic energies, because in this collision there will always be a loss of kinetic energy. So some kinetic energy will be lost, it will go into sound or heat or something else. Because energy is conserved, the law of conservation of energy does not apply to only one form of energy. So energy is conserved, but kinetic energy is not conserved. So it will convert into potential energy, it converts into thermal energy or something else. Within the inelastic collision, you can say it's type A and type B, is what we call the perfectly inelastic collision. In this case, well, the momentum is always conserved. This goes without saying, it's always conserved in all collisions. So sum of Pi equals sum of P final. And the second thing that's here is that the two objects, or whatever number of objects are colliding, the objects stick together in the collision. So they don't hit and bounce off, but they hit each other and they coalesce, or they just join together and move off as one object. So this would be a perfectly inelastic collision. It's the easiest one to solve, and so we'll start off with this kind of collision. the perfectly inelastic collision. Now, in this case, we have the conditions before and after the collision. Before the collision, we have object 1 and we have object 2. And let's consider one-dimensional so that we keep it a little easy for now. The object 1 is moving with the velocity to the right, and let's assume object 2 is also moving with the velocity to the right, but smaller, so that 1 can go and hit number 2. Now we'll take the initial velocities values as u and the final velocities as v. So that way we avoid a subscript. So we'll say that this is u1 and this is u2, and this would be m1 and m2. And after the collision, because we're in 1D, they would stick together and move off with some final velocity. So v1 would be the same as v2, so we just have one final velocity. And now we write the sum of the x momenta initial equals sum of the x momenta final. So this is going to be m1 u1, that's the x component of momentum for p1. Well, since it's 1D, we could just say it's the momentum, and m2 u2. So this would be the initial, and the final would be m1 plus m2, because now it's one object moving with velocity v. So if we know that u1, u2, and m1 and m2, we can find the final velocity. Now let's do an example on this. Let's assume that we have a sort of a track on which we have a toy car, like a train on these tracks, and we have two cars, and by track we mean that it can only go back or forth, and this one has a mass of 2 kilograms and this has 3 kilograms, and this is moving to the right at 5 meters per second, and this is moving to the right at say 3 meters per second. So after some time this is going to come and hit it, but after hitting it, well, it gets locked into it. They just stick together, and so the final condition would be that the two of them would be moving together. So 2 and 3 kilograms, and they would be moving with the same speed v. And now we write the equation: sum of momenta initial equals sum of momenta final. So the initial momentum is the momentum of 1 plus the momentum of 2. It's going to be well, p1x plus p2x initial equals p1 well, x plus p2x final, which is this condition. So this is going to be m1 v1 m1 u1 plus m2 u2, and this is going to be, because they're together, v. So this is going to be 2 times 5, and there's 3 times 3 is 2 plus 3 v. That's 10 and 9. It's 19 divided by 5 is v. That's going to be 3.4 meters per second. So they're both going to go off with a speed that's smaller than this one and faster than this one, somewhere between the two. Now we apply the same thing in the case of a to find the recoil of a gun. So let's suppose that we have a gun, that's the before condition or initial condition, and that's the after or final condition. So we have a gun with a bullet inside it, and they're both at 0, so the speed of the gun is 0, the speed of the bullet is 0, and afterwards the gun is fired, the bullet is going with a large velocity, v bullet, and the gun would recoil backwards. Now let's take some numbers. Let's say the speed of the bullet is 100 meters per second, and that is what we're trying to find. And the mass of the bullet is, let's say, 20 grams, and mass of the gun, let's say 2 kilograms. Then we apply the momentum initial is the sum of the momentum final, both in the x direction because it's actually 1D. So the initial momentum will be mass of the gun, speed of the gun, mass of the bullet, speed of the bullet. On the right hand side, it's going to be mass of the gun, speed of the gun, so the finals are v's and the initials are u's, plus mass of the bullet and speed of the bullet. Now, they're both stationary in the beginning, so this is 0 plus 0, and mass of the gun is 2 kilograms times speed of the gun, which is at the unknown. Mass of the bullet is 20 grams, that's 0.020 kilogram, and speed is 100 meters per second, and therefore V gun is going to bring that on this side. It's going to be minus 2 over 2, so it's going to be minus 1.0 meters per second. So the gun is going to recoil, go backwards at 1 meter per second. So that was a perfectly inelastic collision. Now let's look at inelastic collision. Well, this is somewhat hard to solve unless we know what is the loss of kinetic energy. In the absence of that knowledge, it would be very hard to solve them. So let's look at the earlier example that we did, which was this one. Where we said that this object is moving at 5 meters per second, 2 kilograms, hits a 3 kilogram object, goes off at 4 meters per second at 30 degrees. This goes off at some angle which we did not know. We applied the equation in the x direction and in the y direction, solved it to get this as the velocity. So now let's draw this once again. So we have m1, which is 2 kilograms, moving at 5 meters per second, and m2 was stationary, 3 kilograms, and after the collision it was going at 4 meters per second. That's m2, so 2 kilograms, and the 3 kilogram was going at 1.68 meters per second. So momentum is conserved, that's how we solve it. Now we want to see what happens to the kinetic energy. So this is the initial, this is the final. The initial kinetic energy is going to be the sum of these two. So it's going to be half m1 u1 square plus half m2 u2 square, and this is going to be half m1 is 2, u1 is 5 square, plus u2 is 0, so this is 0, so this becomes 25 joules. On this side, it's going to be half m1 v1 square plus half m2 v2 square, and just remember we do not take the x and y components because kinetic energy is not a vector, it's a scalar, so we just need the velocities. So it's half m1 was 2 and this is 4 square, and half, this is 3, and that's 1.68 square. So this becomes 16, and this becomes 4.23, so that's 20.23. So this equals the final, and this is the initial. So before the collision, the two had 25 joules of kinetic energy, and after the collision, the two have 20.23 joules of kinetic energy. So there's a loss of almost 4.77 joules. Because there's a loss of kinetic energy, this is an inelastic collision. It's not perfectly inelastic because they don't stick together, and we can where does this energy go? Where it goes into sound, into heat, maybe some deformation. Okay, so now we see the last type of collision, which is the elastic collision. Now, in the elastic collision, the momenta are conserved and the kinetic energies are also conserved. Now, we'll again stay with one dimension, and the momentum can be written as, the initial momentum will be m1u1 plus m2u2, and the final will be m1v1 plus m2v2, considering only two particles, and the kinetic energies would be half m1u1 square and half m2u2 square. So that's the kinetic energy of 1 and 2 equals half m1v1 square and half m2v2 square, which is the kinetic energies of the two after the collision. Now this is equation 1, this is equation 2, and it requires some manipulation, after which well, it's all done in the textbook, you can check over there. So just to save some time, I'll just write the final equation. So by manipulating this and using this in it, we can rearrange the second equation to get u1 minus u2 equals v2 minus v1. So the difference in the two velocities before the collision is the same as the difference in the two velocities after the collision, but the sign is changed. So, but the magnitude of the difference of velocities remains the same. Now, this equation is number 3. So we can use equations 1 and 2 to solve the problems, or we can use equations 1 and 3 to solve the problems. This is good because it's only one-dimensional. If we had a 2D problem, we would have an equation for the y direction here for the momentum, and we would not have another equation here because this is not a vector. So we would have 3 equations, and then the problem would be different to solve. So, but this is good for one dimension. Now we can further manipulate equations 1 and 3 to get another equation, or rather another set of equations. And that is V1 in terms of U1 and U2. So it's something times U1 plus something times U2. So if we know the U1 and U2, and inside we'll have the masses, we can get the V1. And we can get the V2 again if we know the U1 and we know the U2. So inside here we have M1 plus M2 in all of them, and here we have M1 minus M2, and here we have M2 minus M1, we have 2M2, and we have 2M1. So we have these two equations. So if we know the masses and the initial velocities, we can get the final velocities through the inelastic collision. through the elastic collision. Now we look at a few special cases, and these cases are all for u2 equals 0. So we have the struck object is stationary and the striking object is going and hitting it with some velocity. And we will consider three cases. So let's keep the equation visible, and let's say the first case is if m1 equals m2. So you have m1 moving with the speed u1 hitting an object 2 same mass which is stationary. What happens after the collision? Well, these two terms are already zeroed because of this condition. If m1 equals m2, this becomes 0 and v1 becomes 0. And v2, if m1 equals m2, this becomes 2m1 and they would cancel, and v2 becomes equal to u1. So after the collision, number 1 would stop and number 2 would move off with a velocity equals u1. And you have seen that in billiards. It goes and hits it and the other ball just takes off. The first one stops right in its tracks if you have a straight head-on collision. If it's not head-on, it will be a 2D problem. The second condition is, let's say if m1 is much bigger than m2. So it's like a big heavy object moving with the velocity u1 hits a small object number 2 which is stationary. What we expect is that m1 is just going to keep on going and it's just going to kick m2 and which is going to fly off. But what happens, let's see here. Well, these two are gone. If m1 is much bigger than m2, we can ignore m2 as compared to m1. We can ignore m2 compared to m1. We'll be left with m1 over m1. We can cancel them out and we'll be left with v1 equals u1. So the speed of 1 after the collision will just be the same as its initial speed. So no change in the speed of the heavy object. v2, the speed of the lighter one. If m1 is much greater than m2, we can ignore this. So we have m1 over m1, which cancel out. We're left with a 2. It's 2u1. So that means that this small one will be going off at 2 times u1. So it's going to go off rather fast. So this is like a heavy bat hitting a stationary ball. So just take a ball, just and swing a bat and hit the ball with a speed, some speed. The ball will move off at twice the speed. Or if you're playing golf and you have the ball sitting here and you swing your golf club and hit it. So if the speed of the golf club is u, the ball should shoot off at 2u, provided the conditions of this are met. Now, third condition is when m1 is much smaller than m2. So you have a tiny object going at a speed v, that's number 1, and hitting a big object, which is stationary. So if m1 is much smaller than m2, so we can ignore m1 compared to m2. This can be ignored. We'll have minus m2 and minus m1. So this is minus 1. So v2 is minus v1 is minus u1. So this is going to bounce back with the same speed. So u1 is going to go backwards with the same speed with which it was coming. So it's just like a ball hitting a wall and bouncing off with the same speed. What happens to m2? So v2, if m2 is much bigger than m1, this is much bigger than m1, we can ignore m1, and a small number divided by a large number gives us a small number. If M2 is very large compared to M1, this is almost 0, so V2 is almost 0. So this will just stay here. So you just hit a big object and bounce back, and this will just almost stay there. So these are a few cases, and we can use these to solve some one-dimensional elastic scattering collisions, elastic collisions.